Hey team, it's Mr. Z, and we're going to continue talking about pipes and drain dimensions. Let's go ahead and dive in and see how this relates to what we were studying. All right, so basically last time we were able to algebraically represent the situation. We took a real life situation and basically we created a formula to find the cross-section area of the drain. This formula basically tells us what we were doing before. It enables us to test a bunch of different dimensions, and we're going to now compare this visually because the skills we have, we can't actually graph this unless we took an extensive amount of effort to do it by hand. But using the technology, that becomes a lot easier. So let's go ahead and look at what some magic Desmos can do. So my function, I'm going to represent it as y. The output is going to be equal to h times 8.5 minus 2h, and then I close my parenthesis. Okay, so remember, this is the output, the y, and if I use function form, they're interchangeable. I started out with y to help you understand that those y coordinates are being created by the input, which is h. The input is not x. X is h in this case, but this is basically saying, like, let's start out here. Let's kind of figure out what we're looking at. So looking at this graph, I don't want it so small, but basically as I go left to right on the graph, the reason why we're not going to really look at the negative parts is, and we're only going to look at this first quadrant, quadrant 1, is because we don't want a height that's negative. So x-axis, the x in this case is height. The height will not be negative. So we're not going to look at this left side of this graph at all because height in real life can't be negative. Here, now looking at the bottom, the output, the y going up, the height, this is not the height, this is the area. Remember, we took base times height is the area. So we took the height times the change that occurs as a result of creating the height. And this formula basically gives us the area. So it's going to organize the area from 0 to 10. We want it positive. The area cannot be negative for this real life object. So we are looking in at this graph, and now understand what we're doing is they're taking a bunch of different situations and they are going to go ahead and try to see which one creates the biggest area. Remember, they would plug in 1, they would plug in 2, they would plug in 3, they would plug in 4, they would figure out 8.5 times 2 times that number, and then they would have to multiply together to compute the area. And then I would scan that list by hand, and that's too much work. The reason I graphically represent this is if I understand that the outputs, the y value is the area, and fixing it this way, it lets me compare it. And this point right here, the vertex of this quadratic, is the maximum area. It is the maximum area because it is the highest point. I can literally see it all above, and there will be nothing beyond this. So what do these numbers mean? Well, 9.031 is the area, the biggest area, while the height is the dimensions that produce the greatest area. So this is like the biggest bang for your buck. If I make sure that the height is very specific, I can get the biggest sewers made for the least amount of material, the maximum, the vertex, hence why we've been studying this. Notice it is a degree 2 because it has 2 roots. I can easily see that it is degree 2, it has 2 x-intercepts. So I know that this is also concave down. All the stuff from the last unit that we've been looking at it algebraically is going to help support the y. But the idea is, hey, what is the xy in this case? And let's jump back. So We're looking at quadrant 1 because we only care. And then it kind of looks like that guy. So I'm going to just be trying to be accurate. 2 and 9 kind of looks like this. And then it's 2.015, 125, comma, 9.031. So there's this maximum. Voila. So let's go back to number, what was it, 4. What is the maximum? Well, looking at the graph, the maximum is 9.031. What are we talking about? Feet, and area is squared. Woo! Like a boss. All right, so now we're going to go ahead and talk about this graph in detail. I would have the Desmos on a phone that you're looking at, and then we're going to go ahead and discuss. So let's dive on in. So what is the maximal cross-sectional area for the drain pipe? And then explain your reasoning. So just don't be intimidated by the language. The cross-sectional area for the drain pipe is basically the sewer that we're looking at. What is the maximal area? Well, what did we say? 9.031. Let me check that. Boom, boom, boom. Now this is feet squared, and the reason being is it is the maximum height. The maximum height Okay, B. Identify and label the intercepts of A of H on your graph. Remember, these zeros are extremely valuable. So, what are they? Well, the x-intercepts. There's 2 because it's a degree 2. It's a quadratic, or 0, 0. And then the other one is 4.25, comma 0. And I do want to draw attention to the fact that it does have a y-intercept. We already described it. It is 0, 0, but the y-intercept has a x that's 0, and the x-intercept has a y that's 0. And let's talk about each. So describe the meaning. This is everyone's favorite part of math class. So what does 0, 0 means? Well, when the height is 0, there is no metal left to bend. When the height is 0, it can be 4.25. Now, identify and label the equation of the axis of symmetry on the graph. Then describe the relationship between the axis of symmetry and the maximal cross-sectional area. So what are we going to look at? We are going to look at the vertex. The vertex is h of k. And remember, it's always going to be x equals the vertex. X equals h. So let's look at my graph. The x value is 2.125. And what this means is that it is going to be the line that cuts it in half. All right, number 8, draw and label the drain with the greatest cross-sectional area. Now, don't do more work than you already did. We are creating a cross-sectional area that's like so. Now, what is going to be the height? Well, we've been saying that the height is 2.125, right? Then we need to know the area is going to be the output, which is 9.031. The area is the inside. And then now you can do some quick math to determine, hey, what is this height? Remember, we described the width in the terms as follows. It is 8.5 minus 2h. So go ahead and take a moment. 8.5 minus 4.25, turning the width to be 4.25. Check for yourself. Does this multiply to be the area? This would be kind of the drain that we would turn in. And I hope this kind of generally helps you. To look at this further, we're going to continue to look at A of H and identify the first factor. Now, I just want you guys to kind of look at this. This is going to be two numbers being multiplied together. Think of this as simply A of H is equal to height times the base. That's how you find the area of a rectangle. You do base times height. This base is a little more complicated to calculate. So the first factor in this equation is the first one is H. H by itself is just a variable. It's degree 1. Remember, it has invisible 1 as the exponent, and this means this is going to be linear. The second factor, 8.5 minus 2h. If I cleverly look at it this way, I hope you can see that this resembles slope-intercept form, meaning that it's going to be linear, which means it's degree 1. Identify the type of function created by the product of both of these. The product is when I multiply both of those together. So what happens when I multiply h and 8.5 minus 2h? Well, let me figure out. I'm going to go ahead and take this and rewrite it in standard form. And I'm going to distribute. Turns into 8.5h minus 2h squared, meaning that it is a degree 2, which means it's a quadratic. Boom. Why does this happen? Because when you multiply the same input by itself, it creates a square, creating the highest exponent, 2. All right, that was the first lesson. Hope this helps. Remember, you can do it.